I think so. Let me make sure.
I will be ready though to use the board. Actually, no one can even
Oh
see.
shoot. Where did it go? No. Okay.
I use a timer because I'm gonna give them 2 minutes. Okay, 4 minutes for each problem, so I want to like time that. We did 2 minutes. Fast. Yeah. No, I mean yeah.
You're good?
Yeah.
You can use my phone for that, I guess.
Okay. Sure. It's okay. I have my phone.
We can just say our names and then get going with the interviews.
Hello? Hello? Hold on.
Hello. Yes, it is.
Okay, we're gonna start now. It's Berkeley time. So this is the CS170 Midterm 1 review session. I'm Denny.
Hello, I'm Perla.
And I'm Max.
And we're going to be leading this review session today. So we're going to do asymptotics and then divide and conquer and FFT. This is all pre-graph material. The review session on Thursday from 8 to 10 p.m. Also, this location is going to be graph material. Questions?
Repeat.
Sorry?
Yes, it is.
Repeat the question.
She's asking whether it's going to be recorded or not. It will be, and it will be posted on Piazza.
Yes. Also, the slides will be posted on Piazza afterwards as well. So, yeah. All right, so we're starting with asymptotics. So, big O means that it's bounded above, and that means if you look at the second graph in B, C, G of n is always above f of n, but that doesn't mean that in the lower area, as you see it earlier in the n part of the graph, it could vary, but as you go to infinity, it should always be above the other one. So big omega means bounded below for the same thing if you look at graph C, and then big theta means it's bounded exactly. So if you have two constants, f of n should be in the middle of those two. So the way we can see what the runtime is we find the limit of the function f of n over g of n, and depending on what it evaluates to, you can see if it's O runtime, theta runtime, or omega runtime. So if f of n is over g of n as the limit goes to infinity is 0, then you know f of n is an element of O of g of n. If it's a constant greater than 0, then you know that f of n is theta g of n. And then lastly, if it's infinity, then we know that f of n is omega g of n. So the way to evaluate the limit if it's not if it has an indeterminate form is you can take the derivative of the top and the bottom and take the limit of that, and that'll be equal to the limit of f of n over g of n, and that's the box on the corner. Okay, Master's theorem. So this is a theorem that you can use on the midterm. It'll help you quickly evaluate runtimes. So if t of n is in the form a t n over b plus o of n to the d. So a, b, and d are constants. A has to be greater than 0, b has to be greater than 1, and d must be greater than or equal to 0. Then t of n equals one of these three, depending on what you evaluate d and log b of a. So if d is greater than log b of a, it's going to be o of n to the d. If d is equal to log b of a, it's o of n to the d log n. And if d is less than log b of a, then it's o of n log b of a. Cool. So we're going to do an exam problem. This is from fall 2018 midterm 1. So it's just a true and false. And I'm going to give you 2 minutes to do these 3 questions, and then we'll come back together. Sorry if that was too fast.
No.
Well, these are things. A little more time. 2 minutes is probably fine. We have more.
Okay. You can just give them 3 minutes. Okay, measure yours to last like 20 minutes.
Okay. I don't think it's going to last 20 minutes.
No, we'll wrap it up. No, mine, I think I'll give them time because I'll also try to take my time. Dividing. So like I'll take my 40 minutes at most. That's like my data.
Explanation for the other 15 minutes.
I'll definitely need more than 2 minutes. Like, I think people are actually waiting for right now, right? So people are like, Yeah, I switched very fast. So I'm hoping I don't do that.
I think I spoke a little bit too fast.
Yes.
But I'll make it up when we get that. I will speak slower.
You were introduced. I guess it's okay because it's not, it's nothing bad.
It's nothing new. That's why I was like,
Yeah.
they're just rules. At least we have to.
Actually, they're asking you.
What was the question? I can't hear it.
Yes, there will be posted. The question was, will the slides be posted? Yes, they will be posted online on Piazza, and they will have the audio too. Was that one?
Yeah. Any other questions? Okay.
I screamed it. I'm sorry.
It is okay.
I forgot that it's webcast. It might be quiet. It's just 10 minutes. Just put it away. I'm gonna get some. I think you should leave them on this therapy. Yeah. We have enough time. Actually, yes. I think we should have 30 more seconds. Definitely coming.
Okay. So we're going to go over the answers now for this question. So n log n is less than or equal to n. So this is true. For number 2, the limit as n goes to infinity of n squared over n log n is infinity. So it is false. And then lastly, 2 to the c log of n is equal to 2 of log n to the c, which is equal to n to the c. So it's true. Any questions on these 3? Okay. All right. Next question is discontinued. So there's 4 more questions. So we'll.
Question here.
Oh, question.
Yeah.
So the question was, will previous exams be posted on the website? I think some of them are posted on the website, but if not, you can look at the HCAN and TBP exam archives if you want to look for past exams. This one was from HCAN, I think. Any other questions? Okay, cool. So work on these 4, and we'll come back to it in 4 minutes.
I just wanted the recording to hear it, so I was like, but I didn't have it. Yeah, no, you're good. You're good. No, you. I think in like a minute. Yeah. I think from this side.
Question. No, I mean, yeah.
You should take it here so they.
Will we be able to hear it from here?
Yeah. No, go there.
I don't know.
Yeah, we should probably just go watch
No. You both. Yeah, they are. And they're more. They're more.
Just the problem.
Right here. They are.
I am my slides. I guess I think we can. A lot of this
I think it's good. Maybe not. Or I don't know.
I think it's a
Yeah, you're right. I mean, I thought we could say no, I didn't. So I knew this.
Okay, we're going to start going over these questions too. So for 4, it's false. It's not always true because, so we have O of log n, but O of log n could be O of like a constant times log n. So we actually could have a function where there's f of n to the c, which is not O of n cubed. C could be greater than 3. So if c was 4, for example, 4 log n would still be would be less than O of log n. Any questions on that one? Okay.
There's a question right here.
Oh, question. Yeah, sure. So if we look at the last slide, we have 2 to the O log 2 of n. So O of log 2 of n means that it has to be, so O of log 2n means that we have to be within log of n, correct? But it could be a constant times log of n, so c log n. So if we have c log n up there instead of just log n, which would still be O of log n, correct? So if we had c log n, we would be able to cancel out log 2 to the log n, and we get n on the bottom, but we get n to the c. C could be a number greater than 3, so then it wouldn't be O of n cubed. Does that make sense? Any other questions on that one? Okay. So for number 5, we can use Master's theorem, and if you plug in everything for A, B, and D, you get that O is theta n log base 150,000, which is O of n to the 2.5. So it's true. 6 is false because for a Master's theorem, you can't say that the recurrence relation is an omega. It has to be an O. And then lastly, if we apply Master's theorem on number 7, we have log b of a equals c, so we get n log n for that one. Yeah, question? So you could use it if it said theta there. The reason why 6 doesn't work is the omega part. Yeah. Oh, sorry. Yeah, I forgot. Oh yeah. So sorry. The question was, is the reason why if 7 had a theta instead of a O, would it still work? And yes, the answer is yes. And then why it's different from 6 is because T of n says omega of n of 2.5, which isn't true for this one. Yeah.
For number 7, is it n log n? Is there like theta n log n?
I think if in lecture it's O. If we look back at the master theorem slide, they use O for every single one. So I would use O. Yeah, question. Sorry, can you hear that? Can you say it a little louder?
For the 7, but you said that if you have n is equals to n log n for the answer, shouldn't it be that if you say if you have n is equals to the O of n log n?
Oh, wait, so you're saying?
So the question was, wouldn't it be better to have big O and log n? And yet the answer is yes.
Oh, okay, yeah. So yes, the question was, wouldn't it be better for the answer to 7 if it was T of n equals O of n log n? And yes, that would be better. I think this was just the answer key from the fall 2018 one, directly pasted into here, but it would be better if it said O in the front. Question?
So if 6 had omega in the recurrence relation, then it would be true, right? If it both of the, if it said 13,000 T of n over 100 plus omega of n, then the statement would be true.
I don't know what the
I think, but usually you don't apply master theorem to omega of, like, the function shouldn't be omega on the other side. It would usually be O.
Your question, like, would it be right if big O of n to the 1.5? Your question, if it's big O of 1.
I think her question was if it was for 6, instead of O of n, if it said omega of n, then would the answer be true? Yeah, so for 6 it's false because you can't guarantee that it's omega of n to the 2.5. Okay, question. If you had to answer it on a test, I think you should use O. Yeah. For true or false. I think.
Ask for clarification.
Oh, okay. Could you clarify that?
No, we should ask for
should I ask for it?
No, like the students should ask for it.
Oh, okay. So the question was, if it says if it says theta on the exam, would it be true or false? So if that happens on the exam, just go up and ask for a clarification.
Yeah.
With the time now for quite a lot. So like it's omega of that rate instead of O. Would be able to
So not necessarily. You can only say that if it's a theta. So if it's theta n to the 2.5, then theta means O and omega. But if it's O, you don't necessarily know what the lower bound is. Yeah. Oh, sorry. Yeah. The question was so since for 5, it's O of n to the 2.5. Can you say that it's omega of 2.5? I think was your question.
I'm saying it for the last term.
Oh, for the
Instead of saying it's O n, I'm saying it's omega. Would Tn be omega? Yeah, omega.
Oh, she's saying if the last term's omega.
So you could say omega of a constant value, but you should not be making conclusions based on a reconciliation equation on other bounds other than big O. I think our point is, whenever you have an equation like this, use the math theorem and stay with the big O. Everything else you have to prove it, and it's case by case. You know,
Yeah. Any other questions on these 4? Okay. So we're gonna move into divide and conquer now.
Hi, so I'll be taking on divide and conquer. So who knows what divide and conquer is? We know, right? Okay. Okay. I did prepare a slide on that. So it's when we have a problem, right? And we make little problems that come from that big problem, and we solve those little problems, and we put the answer together of those with like the actual solution of the bigger problem. That's good. It's pretty recursive idea. So some examples for this is the multiplication with integers, matrix multiplication, polynomial, we just saw FFT in lecture, merge sort, binary search, and a famous one for the past homework, the case largest element search. These are base divide and conquer algorithms that you should have in mind, and you should be very related to them, because as we will see, you will use them, and you saw in the homework, you will use them to solve other problems that are worded differently, but if you modify one of these, you have the solution. Okay, good. So we're gonna do some exam problems. Practice 1. So suppose you're given an array with n elements. It is sorted, and they're integers. And this has been circularly shifted k positions to the right for some k greater or equal than 0. So it can be 0, it can be completely sorted, not shifted, or shifted. The goal is to find the largest element in log n time. I mean, and I want you to provide a brief explanation for this. I do not want a proof of correctness or maybe some pseudocode, but first approach this problem on like main idea. Okay, and here are some examples of the input, like 35, 42, minus 5, and 15, 27, 29. This is a shifted by 2, and then we have a shifted by 4. So this is your input. You do not know k. So you just know that k is some positive, non-negative, actually, integer. Any questions? What are the questions on this problem? Okay, so I'll give you a couple of minutes to approach this problem.
Who knows what divide and conquer is? That's great.
They thought it was a joke. Oh, it was a joke. Asymptotics. It's okay. It's an unintentional joke.
At the second minute, I'll divide it first with n. And then on the second coordinates. I'll try the third hint. After I'll go over the So I will provide a hint on this that I have prepared. So modify a well-known divide and conquer algorithm. This is 2017. So I'll give you a second hint. Modify binary search. They're like, okay, so for now on, I'll give them 2 more minutes. So without giving the answer, can anyone think about a third hint? I think someone had something here. You're saying compare 2 elements in the list and then get rid of something. Kind of binary search, yeah. So yes, so compare the first element with the middle element. This is binary search. But then I guess another hint would be then you have 2 cases, right? You have 2 cases. You're comparing integers, then what happens? I'll give you a minute for this one. Question? I think you want to go. A clarification is that K is not given in the problem. Otherwise, you would rearrange the array and just return the last element. Okay, so I think that's it. So those were the 3 hints. Here's the solution. We have 2 cases. Case 1. The first element is less than or equal than the middle element. Then what do we know about the left side? We know that that left side has to be sorted, right? So we know that no matter what, from the 0th element to the mid element, to the mid -1 element, our max cannot be there. So our mid can be the max, but nothing in between the first element and the mid element. What are the questions on this? Okay, it's clear. So, because we know that we can get rid of that, we get rid of it, and then we recurse on that half. Similarly, for the second case, if the first element is already greater than the middle element, we know that that right side of the array it has to be sorted. So, no matter what, from the first element to the mid minus one element, we're gonna find our max. We cannot just conclude, by the way, that the first element is the max because we don't know about the first element, the second element, and so forth. Notice that you could have also used the last element for this problem. You could have compared the middle element and the last element and do something similar to this. Build up on two cases and... What are the questions for this problem?
I think in case 2, it should say recurse on the left half of 0.
Yes. Yes, so there's a typo in case 2. It says A0 or is in the left half of the array. No, yes. So it should be right.
So this only works if we assume no repeat values, because if there's a lot of repeats, then the mid could be equal to the first detection, correct?
Can you say that again?
This only works if there's no repeat values, because if, for example, the entire second half of the array with the same value as the first, then the mid and the first would be equal.
So what he's saying is that this does not work if they are not distinct values. The first case takes care of this, I believe, because you're saying if the first element is less than or equal than the middle element, right?
Yeah.
So this one takes care of the third case that we will have.
If they're equal, how do you know which side the max is in?
Well, one of them has to be the max. And you store the A middle, or whichever is the max, as your max. You accept it as your max currently. So I say A mid is the max, so I will keep it and keep recursing on the other half. I don't want to get rid of it yet, because of the same point that you made.
But how do you know which half to recurse on if they're equal?
So you're saying A0 and A mid are equal?
Yeah.
If they're equal, then...
The max could be on either side.
Is that true?
Say the areas of each
Zero.
Say the elements of the area.
I guess for this problem, you can assume they're unique. But I will want to try an array where the things are the same and see if it works.
Yeah, okay.
So it doesn't work for you? Okay, so then it's only for unique numbers.
I'm pretty sure you can do it for if they're equal, because if they're equal, then everything from 0 to mid will be equal. So you can put something like that.
Not only will be...
We don't know. The issue is that there's two cases. Either everything from 0 to mid is equal, or everything from mid to the end, and then the first element is equal.
But
We don't
then
know whether or not which case it is.
I want to be 1, 1, 1. So you're saying 1, 1, 1, 1, and then 2, 2, 2. So like the mean, yes, I see your point. So you're saying the A0 and A mid are both 1, but then after the A mid there's a 2. How do you know? That's a good point, yes. So only works for unique. I guess a trick, an edge case, you could say, it might not even work. No, actually, no, I don't want to say that. But yeah, only unique. Okay. Yes. How will you write the explanation for the runtime? You're modifying binary search. And what you're doing in each step is constant. So it's not much different than binary search. So, I mean, when you walk into the exam, because everyone knows what binary search is. And I think you should know the runtime as well of this. And it should be one of those things that you work out the tree or the recurrent relation formula, and you get it out of your using the master's theorem or something. Let's say you forgot about it, which it happens to me. So I mean, it's useful too. Good question. Yeah. So for this one, also, you know you're cutting the array in half every time, only for unique integers, or numbers. So you're getting rid of half the thing. So you're splitting the things by constant term, which is log n. Okay, good. So here's an example. But we didn't use it so far. Practice 2. We have a sort of array, again, of possibly negative. In this case, I made sure there are distinct integers. You want to find out whether there is an index I on which AI, the element on the ith element of the array, equals to the I index. So you want to give a divide and conquer algorithm that runs in log n time. Just think about the main idea for now. And then I'll give you 2 minutes.
I took from last time.
So I'll give you 2 more hints, and the intention is not to be funny. They're actually hints. Yeah.
There could be. I'm not saying. I think but yeah. And it's probably not something here. It's like me and I go up, so I'm like, no, we don't want anything, go ahead and just go. You have to do it. It could be something.
I got it.
Sorry.
Oops.
Are there any questions on the setup of the question? So I will provide a 3rd hint, and then I will go over a small tryout of the problem. So this is the hint. Compare the middle element with the last element, and then recurse accordingly with this. Also, somebody asked, are we going to have to write pseudocode on the exam? You might not. This is, But do focus on the main idea. This is the important part. Is this Python indexing? No. No. The I is positive. Good question. I think they're ready. So here is a brief explanation of the problem. Let's say we have an array like the one on top, and I broke the indexes below. Let's say we try to compare A and 4, right? A, the fourth element, and we have 5 in here. This is not true, right? AI is not equal to I, so there is no way for A5 to equals 5. Why? Yes. Because it's sorted and because they're distinct integers. Because you could have 4 and 5 in a sorted array, but because they're distinct integers, the problem said distinct integers. That's a reason why as well. So, I mean, there's no way for a 5 to be there. There could be a 6, right? But this still doesn't work. So our only hope is for the first element to the third element, and I meant to say 0th element there. 0th to the third element to have the chosen AI equals I. So here is the solution. I just went over an overview of what it is and why it works. What are the questions on this problem? Yes. So you're saying the 5th line? So he's asking, this is a pseudocode, like don't think about, so the question is why is there a minus m in there? Don't think about this as this is like a code notation. It is still recursing on n plus 1 to the n, to n. Sorry, I didn't, yeah, this is some pseudocode.
Won't the runtime no longer be log n if you do an operation and you have to?
Will the runtime not be log n if you do an operation on them?
Like when you subtract m from each element.
So are you asking if you subtract m from this?
In this line, if that's an operation, would it take?
No, if you do it for each element, right? So no, it will not be. So that's definitely a typo with the code. It would not be constant because you're subtracting from each element. So it doesn't seem to me constant. Yeah. Okay, I will move on from this problem. Yes. That's you should be only recursing. I don't know why that is in there, but you should only be recursing on the n plus 1 to the n element. Oh, it's for the indexes to match. She's saying that it's for the indexes to match. Let me see. I don't understand. I'm sorry, I don't know. Can you repeat it?
You repeat it?
So what you do first, like you're recursing from the right side, and you're recursing out like the middle element, and the first element, and then next out.
So she's saying you have to subtract for all of the list to recurse them, to recurse them. That's fine.
Okay, sure.
But I'm not convinced. Do you mind taking this? I'll take her.
I don't.
So I guess what that means is that you're subtracting from the index. However, I was thinking in Python, when you take a subset of an array, that becomes another array and it's 0 index again. That's in Python world, but in this world, it means that you subtract from like the index. to reset it to 0 to the n, to the n plus 1, n minus n plus 1 element. So this is just for indexing purposes. But if you think of Python, you can just remove the n. Good. Okay, I will move on now. This is a harder problem. It involves matrices. So it's about finding a peak element. What is a peak element? A peak element, it's a peak element if it's greater than its 4 neighbors, top, bottom, right, and left. And there can be many peak elements. So think about it as a local maxima instead of a global maximum. And we want to do this in big O rows times log of columns time, and we want to find a peak element, not the peak element. So this is an important clarification. I'll let you read the slides, but after the slide, I have a couple of clarifications that I thought they would be good for this problem because it can be confusing. But I'll let you absorb it. And then.
I think I'm breaking over.
Oh yeah, you want to find the
Just
map?
turn it off more. Because
I will go over some clarifications. So a diagonal adjacent is not considered a neighbor, so we're not thinking of diagonals here. A peak element is not necessarily the maximal element or the maximum, the global maximum. More than one such element can exist, and 4, there will be a peak element. So your main idea, your pseudocode, or whatever it is that you have in mind, should not be just returning not found. Okay.
questions? Oh, shit. Well, he was from the beginning. He was the beginning.
Yeah.
I thought for some reason we missed them before the year. No, I think it's
I have example of inputs for this problem. So given those two matrices, you give that output. I will go back to the slide of the problem statement. Sorry, question?
Is 32 also a valid output?
Yeah.
Yes, just like eight.
So, hello, yeah. So a good way to start this problem, to me this problem was hard, and I attempted it brute force first, and I was like, okay, let's do it brute force. Okay, so this is a brute force approach. It does not work because the runtime is not good enough, right? It's rows times columns, because you're literally going through all the elements of the array. Okay, before I move on to hints, are there any questions on the setup of the problem? Okay, so here's a hint. Find maximum column wise of the middle column. And then I'll give you 2 minutes to approach this. Are there any questions on the hint? So I guess I'm saying we have matrices, get the middle column, find the max in that matrix, and do something with it. Okay, good. I will leave you with that.
explanation of this specific.
Yeah.
Heard it once. It's not going to take yeah, it should be like 5 minutes.
Like a minute. It's probably okay. Okay, hello. Hello. I will provide another hint. Compare with left and right neighbors. If this is a hint.
It is it.
And I will provide another hint on top of this so we can pick a neighbor to recurse on. If you have to recurse on it.
From now, I'm gonna give them like 3 minutes.
So, hello? Someone asked, if I find a big element, do I keep recursing on it? No, you want to return that element because you're done. The goal is just to find a big element. Send it on Slack. It's high attendance. I want to give them another minute actually.
pretty close to the answer. At least 3 people are close to the answer.
Yeah. I mean, sometimes they ask you a question and you have to be very careful of not giving it.
matrix. Instead of giving the answer, I'm going to do this matrix. One more minute and that's the answer. No, don't leave. No.
Hello? So, okay, so without giving the answer, or I mean the hints were closed, does anyone wants to share? Why is this dark?
It's flux, yes.
Or did it crash?
No, it's completely fine. It's time for me to go to sleep.
Okay, so does anyone wants to give anything? If not, we're gonna work this out together with a matrix. So that's the solution, but let's work this out, right? So first thing, what was the first hint? Find the maximum column-wise, right? So we go here to the fourth element on zero indexing. What is the maximum? 24. Then I said compare to the neighbors. So which neighbors do we compare with? Do we compare with the top, bottom, or left and right? I heard like top, right, left. Again. Okay, someone raise their hands and say it. Yes. Left and right. Why? Because, why is that? Why is that? Does you have a question or someone? You can speak.
Because the max has to be like right at the top.
Yeah, because exactly, because we already found the maximum column-wise, so it makes no sense for me to compare top or right, top or bottom. Okay, so yes.
What's the runtime of finding the maximum?
N. Log N? What do you mean? Oh, I'm sorry. I mean, if you think about, huh? It's N, yeah.
The length of the column.
The length of the column, but I mean, let's assume this is a square matrix, which is not, but in general, n by m, which will be, I mean, like rows, right? Actually, yes, that's actually accurate, rows. Yeah, it would take rows. Yep. So after we compare with the left and right, what do we do? Which one do we pick? Which one do you want to go on to? Someone said the maximum, yes. Why is this? Yeah, it is because, I mean, obviously you're not gonna, so think about if you're going on a like a mountain, is that? Mountain? If you're going on a mountain, right, you're going up. You're trying to find a local maximum. You don't want to go down, right? That does make no sense. So you're trying to go up, you're gonna hike, you're trying to go up. So yes, you will recurse on 31. From 31, by the way, what do you do with the rest of the matrix? You get rid of it, right? You throw it away. Because the 31 neighbor, the neighbor 31, that could be the local maximum, sorry, or something else on the other one. Why? This is a proof of correctness thing to do, but there is an easy way to observe this. There was the fourth one, there will always be a peak element. When you split the array, the matrix, what you're left with, it's another matrix. Induction, right? So you will, because of this fact, if you prove the fact, which I will not right now, but if you prove the fact that there has to be a peak element, then what you're left with is another matrix. And so there has to be a peak element there too. So that's why it works. Question. The question was, what is the significance of using the maximum of column? Good question. The significance of this is you want to get rid of the fact that the top and bottom neighbors. So you want to make sure the one that you picked is greater than the top and bottom neighbors. And you want to pick the middle one. You want to pick the middle column to find the max on, and then recurse, because it's kind of like my binary search. It's targeting your yeah. So you're saying, what if above 24 there was a bigger element? Diagonal 9, 15. Okay, she's asking, good question. She's asking, you found 24. And what if the 9 and the 31 were switched? You would recurse on which one? On the 14, right? Again. Yes. And that's still fine, because you want to find a peak element. And by this fact, which says there will be a peak element on that side of the array, you might not think, you will not pick 31, right? But you will pick a peak element. Yeah. Well, because you're digging upwards. Yeah. So she's saying, what is the point of going to the higher neighbor? Well, like I said, we're trying to go upward on your direction. You don't want to go downward. Yes.
How do you know that this idea recurs on? How do you know that there's like one
You're saying, what if?
What if there's only one going Does it always say that?
Oh, okay. He's asking, what if there is one peak element? You should try it out. You will see that you will end up, this would only happen if they're all equal, right? Or I guess those are edge cases. It depends on how you want to define a peak element, if it's greater or equal. But you were going to say something. But if it's unique, it will find out. But I don't think it can be. I cannot hear you.
What if the top neighbor of 31 was like 33? How would we recurse? Are we going to go to the right neighbor or left?
So yes, yeah. Okay, good question. He's saying, what if 32 was in the place of 9? You can see it on the 5th column, the first row, 9. Okay, so this is recursive, right? So when you recurse on the 31 side, you will not start from the 31 column. You'll start from the middle column, which is 12. And then you will keep going and do your algorithm, so on. Yes?
So, you're saying that even if it's a matrix, then there must be it, right?
Yeah.
And it doesn't matter if my equation on the left side or the right side.
It does matter, because you want to go higher. You want to climb a mountain, not. And you also want to keep consistency, right?
Even if it goes recursive on the left side, you will find a neighbor.
No, it will not work. If you go to the minimum neighbor, it would not work. What if the minimum side has all 2s, and you pick that one instead of, there was a 3 here, and that was the peak element because there was all 1s in the other side and a 3. Then it would not work. One more question? Yes.
How rigorously should we prove that there's always a peak element?
the question is, how rigorous should we be with our proof of correctness? A tip that I give, don't take this to heart, but I think focus on your main idea first. On the exam, focus on the main idea, and then find something like when you're trying to prove, then question yourself, why is it that it is this way? And then you should arrive with a statement like the fourth statement, and then prove it. You should first convince yourself, right, that it works. That's why the main idea is very important. So that's everything I have prepared for you. We'll take on fast Fourier transform. Thank you.
Okay, so we're going to move on to fast Fourier transform. Okay. So the ultimate goal for fast Fourier transform is to multiply together two polynomials. And so for our brute force algorithm, we're going to multiply every single element from the first polynomial with every single element in the second polynomial. And so the algorithm for this one will be O of n squared, which is slower than fast Fourier transform. So by definition, a polynomial of degree d is uniquely determined by d plus 1 points. So that means we could represent the polynomial in its coefficient form. So this one's dCBA. Or we could evaluate the polynomial at d plus 1 points, which is 4, and at like 1, 2, 3, and 4, and that would be called value form. So polynomial multiplication in value form takes n times. So why is that? So say we have two polynomials, p of x and q of x. They're both of degree 2. We want to find the value form of r of x, which is p of x times q of x. So r of x needs at least 5 points. We know this because r of x is equal to p of x times q of x. So a degree 2 polynomial multiplied by a degree 2 polynomial will give us a degree 4 polynomial. So we'll need 5 points. And so if we're given the evaluation of P1, Q1, P2, Q2, all the way up to P1, P5 and Q5, we can find R1, R2, R3, R4, R5 in linear time because we know that R1 is equal to P1 times Q1, R2 is equal to P2 times Q2, etc. So it'll take us n time.
All right, these next slides are handcrafted, homegrown, so we'll see how it goes by me. So first, for FFT, it's important to talk about kind of what are the values that we're evaluating it on. We care about the complex numbers, but this is an entire plane. For FFT, we really only care about complex numbers on the circle. We say they have magnitude 1. And the main operation we have for complex numbers on the circle is multiplying them. So in this example, we have A, which is some complex number on the circle, and B, similarly. We can define those numbers by having an angle, theta 1, theta 2. You can think about this angle as a fraction around the circle. We'll see that in a second. And then when we multiply these, as with the blue AB, it's basically just adding the angles. That is our rule for multiplying complex numbers. So this is it pictured more visually. If we go around A and then we go around B, multiplying is the same as going around both A and B. So if A is going a quarter around the circle, B 2/5, we just add them together like fractions. And similarly, the same thing happens when we multiply with the exponent notation. So it all kind of fits together quite nicely. I think this is the best way to think about, you know, the big, like the omegas, which can be quite confusing. Just think about it as turns around the circle. Do we have questions about that? Okay, cool. So an nth root of unity has a special property, but we can just think about it as one of these complex numbers on the circle, and it goes around a certain way, a certain fraction around the circle. So what we want is, if we do that same fraction n times, we will go around the whole way. So we will eventually end up back at 1. We will have e to the 2 pi I, and that will just equal 0, because if we go, you know, the entire way around the circle, that would be just ending up in the same place. So for some examples, I just drew some of the first roots of unity. So here we have the two roots of unity. Every root of unity looks like this, basically. We have e to the some power, and then we take it to some exponent, and we'll see like the general form in a second. But you know, on the right we have 1, which I wrote in a different way, and we have going halfway around the circle, which I wrote also in a more complicated way, but we'll see why that will be important. So we can keep going. For the third roots of unity, we're going a third, then 2/3, then the full way around the circle. And this is the roots picture. Same thing for the fourth roots of unity, fifth roots of unity. You can kind of keep going as many roots of unity as you want. And we'll do this when we're looking at the fast Fourier transform. So in general, for some n, we have n roots of unity. And this is what they are. We start at e to the 2 pi I, and then our fraction will be 0, meaning we literally just are at the same place we started at. We didn't move at all. We go 1 over n turns, we go 2 over n turns, and we go all the way up to n minus 1 over n turns. So as a quick question, why didn't I include e to the 2 pi I times n over n? Why isn't that a root of unity that I put here? I already included it. That's the answer. That's basically going back to the same place we started at. So even though the angle is different, the angle is exactly 2 pi added to one of these other angles, so it really is the same complex number for all our purposes. So the property that these roots have is if we exponentiate them, if we take them to the nth power, for any nth root of unity, we take it to the nth power. I have a little bit of mathematical simplification, but it basically just ends up at 1. So put in graphical terms, if we go around the circle enough times, if we do this enough times, then we get back to the start. So now let's look at what the FFT actually does. In the general form, we have a polynomial, and we have it, as Jenny was explaining, in coefficient form, and we want to convert it to value form. So typically we'll have a degree n polynomial, here n is 3, and we'll have to have it, the number of coefficients is going to be n plus 1, and similarly the number of values we expect from FFT is also n plus 1. So this is what FFT is doing. You can think about this more formally. FFT is really a linear transformation. It has a special matrix, which we call a van der Waals matrix. There's all this amazing math around it. But I think for the purposes of the exam and understanding what FFT is, that's not too important. What is important is that FFT is its own inverse up to a constant. So if we run FFT on the value form of a polynomial, we receive the coefficient form. Not exactly. We need to divide out by n. That's my clarification here, up to 1 over n. But other than that, FFT is its own inverse. Question?
Are the x's on the right and left-hand side there referring to the same? Because I would have thought the x's on the right is like the primitive root of unity or whatever, and the x's on the left are,
Okay.
the left, right, the same.
So the question is, what's the difference between the x on the left-hand side and the right-hand side? That's actually a really good point. So on the right-hand side, x is just some number. Let's call it like 3. And then we're going to evaluate p at 3, 9, 27, and 81. And on the left-hand side, x is a formal symbol I'm using to represent the polynomial in its coefficient form. Yeah, so those are 2 different x's. That's a good question. Hopefully people understand that explanation. Like, it's 2 different x's. On the right, we're talking about a specific x. On the left-hand side, we're just talking about the polynomial itself. We're not evaluating it on any values. All right. So this takes us to our algorithm for polynomial multiplication, which is basically the standard way to do it would take n squared time in the degree of the polynomials, right? But what we can do instead is we run FFT in parallel on P and Q, or input polynomials, and then we multiply the values together. So we multiply P of x with Q of x, P of x squared with Q of x squared, and then we receive all those values just as a big list. And then we finally run FFT again, and as we talked about before, FFT is its own inverse, so what this will do is it converts from the value form of the product back to the coefficient form of the product. So we end up with this really nice thing where we can just multiply by value, which is way easier than multiplying by coefficient. It's a really magical thing. We kind of change basis and everything becomes easier. That's the main idea behind this algorithm. Yeah, question?
The inverse of FFT, like
So the question is, the inverse of f of t involves omega to the negative power. So I guess you're asking more like formally mathematically what the actual matrix looks like for the linear transformation. Yes, you can derive it by saying omega to the negative first power, but if you work it out, you can actually see that the matrix is, the technical name is conjugate transpose, but it's very similar to the original matrix that we have. And that's what I mean by running f of t again. It's basically using the same matrix. I think you can look in the textbook for like a more detailed explanation of what happens for the f of t negative 1. But yeah, that's a good starting point for it. Other questions? All right, awesome. So then let's look at how we actually run f of t for a polynomial. The amazing observation we have is that the coefficient form of a polynomial can be split up into 2 different pieces. So let's run it for a 3rd degree polynomial. We're going to have 4 points. Let's split it up half. Half will take the evens, half will take the odds, and we can kind of decompose it this way. We can write this polynomial as a sum of 2 degree 1 polynomials, each with 2 data points. And this is really important because, as we know in divide and conquer, you want to reduce the size of the problem before kind of recursing, right? So what we notice is, to compute f of t on p of x, remember that this is evaluating it on these powers of x. We need 8 pieces of information so far, right? We need to evaluate a on x squared, x fourth, x to the 6th, x to the 8th, and same for b. So this is kind of turning into a problem that's not getting any smaller. We originally wanted 4 values of p, and now we need to evaluate 8 values for a and b combined. But the magic step is, what if we set x, the thing we're evaluating on, to be our omega, or one of the roots of unity? So we pick the root of unity to be the same as 1 plus the degree of the polynomial in question, and we'll see why in just a moment. When we take that to the 4th power, we end up with 1. So what ends up happening is, previously we had x to the 4th, x to the 6th, x to the 8th. When we go x to the 4th, that's just doing a complete rotation around the circle, so this becomes 1. So it turns out that we only need to find 4 pieces of information. We started with 4, and we still only need 4, except now we're running the algorithm twice on 2 smaller polynomials. This is like a crucial step, so if people have questions, now is a great time to ask. Yeah?
Can you explain why you have to find A1 and B1?
So we need to find these because we wrote P as a sum of A and B. So finding those will help us find the answer for what P evaluated at remember the original problem for f of t, we want to evaluate P at 4 points. So that's kind of the information we need to compute it. Good question. Any other questions? All right. So what we can notice is that if we take omega squared, this is also a root of unity. It's just a half root of unity, right? If we have a 4th root of unity, which is I, we square it, we get -1. So in other words, finding a of omega squared and a of 1, b of omega squared, b of 1 is exactly the same as calling f of t with the polynomial a, and we feed in omega squared. And we also call f of t on the polynomial b, and we feed in omega squared. So this is exactly our divide step. We can recursively call f of t twice on 2 smaller polynomials, and omega is getting bigger. Omega is getting closer to 1. So in fact, when omega is 1, we basically have no more work to do. So we can draw that out as a tree. At the very top of the tree, we have our original polynomial, and then this is kind of the work we need to do, right? We've seen this tree before, maybe in 621b, even in this class. This is the work we need to do at each level. So at each level, we're going to split the polynomial into 2 pieces and also run f of t on those pieces. So if we count the total amount of work, we have omega at the very top is what we're plugging in, omega squared at the 2nd level, omega to the 4th on the 3rd level, and the degree of the polynomial is halving each time. So the total amount of work we have to do at each level is going to be n, but the number of levels is going to be having n at each level. So we're only going to have n, log n levels. So that means that the total runtime is n log n. Questions on that? All right, so let's do some practice. DFT is just another synonym for running the FFT operation. So find the Fourier transform on this polynomial. It's discrete Fourier. It's technically it's the operation, and FFT is an algorithm, but it doesn't make a big difference.
It's fine, I think my brain has nothing. So I don't know why are they even here. You know why? Because you have to put it here. If you breathe, it doesn't go to the microphone because we're holding it here. We breathe and it goes to the microphone. So you want to go like this. It just, we're too late. Not too late. Recording.
Yeah, about 7 seconds. I have 3.
Give them enough time. I just feel like at this point we're like they're tired. It's 9:30. Some people are tired.
They're still working. Wait until people.
Yeah. Once you see all the heads up, not all of them.
These people are stuck.
Or not. Yeah. Is that your candy? I want candy.
Candy.
Yeah, is that yours? Oh, it's not yours, right? Oh, so yeah, I want to eat it. I did eat a lot of candy. There's so much food.
6 hours.
So, I'm gonna make an announcement again, like, it's like a midterm. They don't prepare. Just remind them, like, yeah. Oh, yeah, you do. Yeah, that's true. If you're doing this work, yeah, let me take my back. It's my fault. Oh, that's my yeah.
Minus levels. Minus levels.
You're the best according to
State material.
that. It's really sad. So are these like animals? Yeah. They're not animals? Sales.
Sales. Like what is sale? Okay. Let me ask you a question.
That's not an animal. Okay, good. It's vegan. Should I call Max? Yeah. I guess he's trying to like elongate the time as well, but it's fine. Let's take our time. I think it might actually run out of time. Max? Actually, I'll go. Okay.
Okay. All right, so let's go over the solution to this one. May I have everyone's attention, please? Everyone's attention, please.
Fine, just quiet down and they'll quiet down eventually. You see like this.
Okay. All right. So this is the answer. I will explain what is going on, but the basic idea is we take the representation we already have, and the way we phrase this in terms of linear algebra, sorry, I can't speak if other people are talking. Okay, thank you. So what we do is we convert to a vector representation, which is basically just listing out the coefficients of the polynomial. So for p, it's going to be 2, 1, 3, 4. And then we multiply it by this matrix. But all that operation means, you can think about it, each row of the resulting vector is going to be the dot product between the same row in the matrix with the entire coefficient vector. So the first row is actually evaluating the polynomial at 2, 1, 4, 3, or sorry, at omega equals 1. And then the next row is going to be evaluating it for the square of that, and so on. Yeah, question? Okay, so I've heard this from other people. So you can define the f of t. The order doesn't really matter. So there's two matrices we care about. There's the f of t and there's its inverse, right? So for the homework solutions, I've also heard that people, the first matrix we use is defined as the inverse matrix. But it actually doesn't really matter if you're doing polynomial multiplication, right? Because f of t and f of t inverse are the same. And it's basically doing the exact same thing. It's just evaluating it at a different value of omega. I want to say that the convention is to start with the f of t matrix, not its inverse, if we want to convert to another representation. Yeah, question?
Shouldn't the fourth item, the second row, have matrix be an I?
Probably, yes. I can't check it up here. I cubed. Yes, okay, you're right, yes. So as a clarification.
The point of the problem is to f of t is matrix multiplication.
Yeah. So the point of the problem is f of t matrix multiplication. The details are not that important. Yes, question, Richard? Sorry, 1 second. Can people please quiet down so I can hear the question?
So in the textbook, it uses omega equals I theta. In this case, it's omega equals e to the minus I theta. So like those two don't matter.
Yes. Yeah, so the order doesn't matter if you're doing the polynomial multiplication. It should be clear on an exam like what omega you should use, and if it's not, ask for clarification. So people won't ask you to like run DFT without the convention. But I would assume take it for omega, like e to the 2 pi I positive. Yes. Okay.
In general, use the convention of the book, because then if you do that one, you can go to the creator and say like, I use this, and I mean that's what it says.
Yeah. Use the convention of the book.
Yeah.
Yes. Question. Yeah. Can we talk about that after? I don't really have a good way to write, but the formula is basically the ij. So the element at row I, column j, will be omega to the ij. That's like the quick formula, and that omega is like your root of unity, which could be favored. It could be the positive or negative, as other people were discussing. Other questions?
Next question.
Yeah.
How does this matrix multiplication take less than n squared?
We were talking about that when we were talking about the fast Fourier transform algorithm, but the basic idea is we can divide the subproblem and we can exploit the structure given by the fact that these are roots of unity, not just any old values that we're evaluating on. The textbook has a good explanation on this. I also explained in the past slides how we end up with an n log n runtime instead of an n squared. Yeah, and I think it's also explained in lecture 2. That's just a variety of sources.
That's just reiterate, evaluate it for roots of unity and then
Yeah, so again, the point of this question is we evaluate it at 4 roots of unity, and then that gives us our value representation. All right? So the next question is to find the inverse DFT of this polynomial.
Tell them you'll give them a question.
Yeah. Question.
So what omega
So I assumed we took omega to be e to the negative 2 pi I over 4. Yeah. And you also have to be careful with the constant multiple in front. But yeah.
we're not using the negative version, right? We're using the positive version.
Yeah, it's confusing too. Like,
Because the other class uses the negative version.
so we're doing interpolation, right?
Yes. So well, in this one, yeah.
So this is FFT, coefficient representation. The previous one was coefficient representation.
Yes.
Yeah, it's positive.
Yes, it is positive.
It should be positive.
You should explain this formula.
Uh,
Or maybe not.
I cannot.
No, it's fine.
Yeah.
We should have mentioned that.
I think it's fine. I think it's just a question. And it has the same matrix here. That's fine.
Yeah, I think I'm gonna write that down.
So for finding the inverse DFT, we do something very similar. Again, I know there's questions on sign convention and all of that, but the basic idea is we multiply by a matrix. We have to correct with a coefficient to make sure that the matrices are actually inverses of each other. But the idea is, again, we're multiplying by a special matrix. Convention can be given in the textbook. Questions about that? Yeah. Yeah, so another question is, should we be multiplying by the values, the points? And the idea is really that the data is the same. We still have 4 points of data, regardless of our initial object that we're dealing with. So if the object is a polynomial, it's still 4 points of data in this problem. We can consider those points as values or coefficients, whatever we want.
It's all our topics.
Yeah, question. Sorry, could people quiet down again? Thanks. So the inverse matrix is almost exactly the same matrix. It depends on our formulation, but this constant factor, if that's what you're asking about, this constant factor is to make sure that the DFT operation, if we do the DFT and then the opposite matrix, that it ends up in the same spot. Does that answer your question? No? Okay. Yes. Yeah, so you can consider the matrix as the conjugate transpose, and it looks extremely similar. It's just our omega, we can consider it to be another root of unity. But the structure of the matrix is the same. Okay, question?
Do you use the inverse of the matrix and when you're dealing with polynomial coefficients and normal one by points?
Yeah, so it's a similar confusion, but the idea of this question is DFT by itself is just an operation we run on data. So the idea is we have to first convert the data into a vector form. You're right that if we were doing polynomial multiplication, for instance, then we wouldn't be doing this necessarily. We would be running it on the values that P has. But now we're just considering P as its own vector in coefficient form. For this problem. Like in the scope of DFT in general, we would be running inverse DFT on the value representation. We wouldn't be doing it in the case of polynomial multiplication. That's like the canonical application of DFT. For this problem, that's what we're doing, but in general, I would say we don't do that. Okay. I understand that there's a lot of confusion about like convention and notation. Perla wrote on this board here that we have, this is our F18 matrix that we convert. So the inverse of this matrix is going to be, this is our 1 over n constant factor, and then we have omega to the negative 1. So the structure of the matrix is very similar. We're just using the inverse omega as opposed to omega. Yeah, okay.
So someone asked whether we want to have coefficients at the end. Notice that this is a degree 2 polynomial, and we have like 4 things there. Yes, you do need them because you want, well, first the matrix multiplication has to work, and second, you need t plus 1 roots of unity, at least. And you can only go up to 4, so you need the last one. Okay, good.
All right, so we will move on to the next question, just because I'd like to do this one. So using FFT, I know there's an easier way to compute this product just by multiplying the two polynomials together formally, but try to do this using the DFT instead. It's like there's 2 conventions, and each person picked a convention, and I have to like, yeah.
I felt like your omega would be wherever it was like when you got back to omega was 0
Yeah. So that may have been a mistake. So for taking the FFT going forward, but let's say to convert from coefficient to value representation, if we want to evaluate the matrix on, like really the order doesn't matter. Like the order, I mean using omega to the 1 or negative 1. The convention is...
So you're going to hit all of those eventually, so you're going to evaluate here, 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 and here, right? So on the test, use the positive way, so don't do negative either, use either. Yeah, because that's what it says in the textbook, and that's how Rao and Chandler taught it. So I would use the positive way. It just means you're rotating this way instead of the other way. Yeah. But just like what I noticed was like each tuning was switched. Yeah, like negative.
Yeah.
So like when would I use it? Why? Like I'm just curious, like why is like negative y? It actually really doesn't matter because If you do negative I, it just means you're rotating this way, and then if you use I, you're rotating this way. But you're going to hit all the 4 roots of unity either way.
Okay, so then this is the value representation.
Yeah, it's just the order of the values is shifting. So as Jenny said, we're rotating. The order of the values in this case is shifting. Like that's just
because you start at 0, so you start at 0 in both cases, right? Then if you go in the negative way, or sorry for you, you start at 0, right? If you go in the negative way, you're going to go down, and then here and then up. So you get this one, this one, this one, this one, right?
Like these two would stay.
Exactly. Does that make sense?
okay. Let me finish
so
this
the
off.
order technically.
I can feel this session collapsing on itself. So. Okay, so we're almost at the end. Let's just finish this off. So the solution I am giving, we run it for the 2 by 2 case, and we end up with this representation. And we do that for the other polynomial as well. And then we take the product between these. And then we will want to run the inverse DFT on that. Does anyone spot a problem with what I just did? Someone raised their hand. Yes. Yes, exactly. So the mistake I just made, which is an extremely common mistake, is that the vector I have ending here, I'm expecting a degree up to degree 2 polynomial, which will mean I need a 4-length vector. But this 2-length vector is only going to give me 2 data points. I will need at least 3. So what I actually want to do at the beginning, instead of evaluating DFT on the 2-length vectors, I want to evaluate it on 4-length vectors so I can get more information, and then I do the multiplication with 4-length vectors instead. And the process would look very similar to what we looked at in the previous problem. But then we would finally come to an answer that kind of makes sense. So this is a really common pitfall. But the idea is deal with the largest polynomial in your problem and add 1 to the degree. That should be like the size of the DFT that you should be running. Questions on that?
Is there a correct solution to that?
This is where the slides end. So, but really, it's the same principle as the other problems. The solution is given by actually multiplying the polynomials. The idea is just to get the procedure right for DFT. Yeah, that is where we will end it. Thank you everyone for coming. We have a review session on graphs on Thursday in this room, 8 to 10 p.m. Come to that too. It will be very informative and will raise your score on the midterm.
No, I don't know.
Not guaranteed, but correlated.
You don't add 1, right? Isn't DFT always a power of 2?
Yeah, you pad it up to the next power of 2 that is higher than.
Okay, I didn't think that was clarified. I thought he just said add 1.
You, hello. You go up to the next roots of unity. You don't go only 1. You go to the next one.
Oh my God.
So if that is 16, whatever it is, the next one, you go up to that one. That's a important fact of life. Yeah.